Let's hope for the best here. We're going to work with vectors. Vectors in this class are going to be defined as something with magnitude and direction. Let's look at a few examples of different concepts that maybe you've encountered in a physics class or maybe in a math class. A scalar is something that's just represented by a single number. So if you're driving maybe, I don't know, 70 miles an hour on the off-ramp or something like that, then that's just a speed. It's not telling you where you're going. It's not saying 75 miles an hour north or 70 miles an hour south. It's just a speed. So that would be a scalar quantity. What about temperature? Is temperature a scalar or a vector? Does temperature have magnitude and direction? Now, there's no direction for temperature, so again, that's a scalar. Velocity is different than speed. Your velocity implies you have a speed and a direction. So velocity is a vector, and this last one is kind of like, as subtle as a brick. Magnitude and direction of a force. Is that a scalar or? Yeah, all right. So that one's a little bit forced, but it's a vector. There's two quantities, magnitude and direction. Let's take a look at forming a point, or take a look at what direction or vectors are going to be for us in this section. We've got 2 points, one at the origin and one down here at -3, -5. But that's just 2 points. If I join those 2 points, that's when I can get a vector. The vector PQ says, all right, we're going to start out here at the origin and move this far in this direction. So I'll move to that point. And so this would be the magnitude, or excuse me, this would be the vector PQ, -3, -5. Now what's the difference between the point -3, -5 and this? Some notation. You've got angled brackets. Those angled brackets reflect the fact that you've got something that starts out at the origin and moves to here. How do you find vectors? How could you calculate a vector? Well, let's take a look at problem number 30, which asks us to calculate a vector that's parallel to this one. So let me give you the coordinates that are relevant to problem number 30. So in problem 30, we've got a point at -3 and 2, and another point up here at 6 and 5. So we'll call the initial point P. So this is P and this is Q. If I want to form a a vector PQ, then PQ is going to equal the difference between these two. You're going to subtract the coordinates kind of term by term, Q minus P. So PQ is going to be 6 minus -3, and then 5 minus 2. Of course, that simplifies. Hopefully you see what I've got here. I've got a vector with coordinates of 9 and 3. Now sometimes put a little arrow like this, meaning you're starting out here and you're ending up here. That's a notation I'm not really going to bother you with too much. But let's draw this. 9 and 3. So 9 is out here, up 3. In fact, it's already kind of partially drawn for you. The only thing left then is to sketch in the actual magnitude here. Right there. And this is vector PQ. These are considered parallel. They're equivalent vectors. They both have the same magnitude and direction. So if I pick this up and put it here, I could start out at the origin and get here. Or if I pick this one up, put it here, I'll start out at P and get to Q. They're parallel vectors. They're essentially the same. let's continue working with vectors a little bit. Are we okay with this notation here? Some of this initial stuff?
So 9 and 3, this new vector that you just put, is that kind of like an equivalent to like 9 and 3 and 0, 0?
Yeah, I mean, it could be thought of as 9 minus 0 and 3 minus 0. That is, if you had an initial point here at 0, 0 and a terminal point at 9, 3, if you subtracted these, you'd get a vector with components of 9 and 3. So it's the same magnitude and direction as what we have here. And these two vectors are equivalent. They have the same magnitude, same direction. Now, I've been using this term of magnitude kind of casually. The magnitude is going to be the length of this vector. So how would you find the length of PQ? Pythagorean theorem. Yeah, good. So that's it in general. If you have a vector v with components of, say, a and b, and let's draw ourselves such a vector. So this is a, this is a height of b, then the length of this is just going to be given from the Pythagorean theorem. So we call that the length. It has this special notation. It looks like a double absolute value is what it looks like. But the magnitude of v is just going to be the square root of a squared plus b squared. And it comes directly from the Pythagorean theorem. Yeah, please. Oh, I'm just drawing a general A and B. It doesn't necessarily I'm not trying to reflect actual numbers here. Yeah, no, I appreciate the question. But we will put in some numbers, though. Let's find the magnitude and direction for a problem like number 40. And another quick comment on notation. Sometimes we work with special vectors called I and j. So let me comment on those real quick before we get into problem 40 so that maybe we can understand problem 40 when we see it. I is the vector 1, 0. And j is going to be the opposite vector, 0, 1. J is 0, 1. These are going to be called unit vectors because their length is just 1. But when we're working with certain vectors, then, like problem number 40, we can use these to express them in different ways. For instance, if I had the vector 6, 2, I could think of that as the vector 6, 0 plus the vector 0, 2, splitting them up. Or I could think of it as 6 times 1, 0 plus 2 times 0, 1. Or better yet, 6i plus 2j. And it's just a different way to write the vector. This and this are totally equivalent. Sometimes people find it more convenient to write it this way. Sometimes people use it this way. It doesn't matter. Both of them express the same thing. Either way, if this is vector v, let's see if we can't find the length of vector v. I'm going to go back to this notation here. This notation here works as well. This is your a and this is your b in the formula the square root of a squared plus b squared. 6 squared plus 2 squared gives me 40. I'm not really concerned about whether or not you want to simplify it by writing it as 4 times 10 and the square root of 4 is 2. I mostly care about the square root of 40. That's the important part that I want you to see. Let's try a couple follow-ups to that. Are you okay with this first one here, number 40? Nothing too taxing on that one?
Just a question. What is the symbol with the V front? Absolute value, what is it?
You'll hear me call it a couple different things. When I'm thinking about it carefully, I'll call it the length. And when I'm not thinking about it carefully, I'll revert to a different terminology for it. I'll call it the norm. This is not the guy in Cheers, sat on the bench and drank a lot of beer. It's NORM. It's another way of saying the magnitude. Probably it's a little bit more general. All right, but I'll try and use length because that's what it is. I want to keep this friendly. Let's try problem number 44 and 46. They're going to kind of go together, and they're going to demonstrate something called the triangle inequality. In both of these, we'll use the following definitions. V is going to be 3i minus 5j. And W is going to be negative 2i plus 3j. Problem 42 asks us to calculate the length of V plus W. Problem 44 asks us to calculate the length of V plus the length of W. Do you think these are going to be the same? Got to vote for no? Okay. Let's find out what happens. What do I have to do here first with problem number 44? I've got to add these two together. Now, if you want to add them together like this, or if you prefer this notation, negative or 3, negative 5, and negative 2 and 3, it's up to you. But let's think. If I add V plus W, it's going to be 3 plus negative 2. That's going to be 1. Negative 5 plus 3 is going to be negative 2. So 1 plus negative 2 times I, or it's negative 2 times j. The length of this would be the square root of 1 squared plus negative 2 squared is the square root of 5. Why don't you see if you can't calculate the other one, problem number 44. Find the length of W and add it to the length of V. So use 3 squared plus negative 5 squared, and then add them together to the square So let's take a look at this one here. V, where was V? Well, V was right here. It had two components, 3 and 5. That's your A and B. So to calculate its length, it's going to be the square root of 3 squared plus negative 5 squared. 9 plus 25 gives you the square root of 34. That's it. We're going to do the same thing with W. Here's your A, here's your B. And I'm referring back to this formula right here. Once you've got A and B, or you could write this, similarly as AI plus this term here, then it's still the same thing. Square root of negative 2 squared plus 3 squared. 4 and 9 gives you 13. Okay. Let me give you a little geometric interpretation for this. If you have two vectors, say A and B, and you add them together, kind of put them together, you get a triangle. So here's vector V, and here's vector W. What the triangle inequality is saying is this, or I haven't written it down yet, but this is V plus W. It's the sum of adding those two together. And I could draw this differently, but I've drawn it to show a little bit of a triangle. When you add up these two sides, any two sides of a triangle have to be longer than the third side. That's what's going on here. And if I write this down in general, the length of V plus W is always less than or equal to the length of V plus the length of W. The length of two sides of the triangle is always greater than that third side. That's what it's saying. Triangle inequality. The only time it would be equal is if everything pointed in the same direction. As if you had, V was this way and W was this way, if they're all on the same line. In that case, you wouldn't really even have a triangle. It would just be a straight line. Okay, let's skip that for a second. Coming back to here. Are we okay with the calculation of the distance of something? Earlier I mentioned that I and j were unit vectors. Let's understand why. If we actually calculate the length of this, let's find the length of I. So the length of I would be the square root of 1 squared plus 0 squared, which is 1. I equaling 1, 0. So I and j are, like I said, called unit vectors. Sometimes you want to create a unit vector in a certain direction, and we can do that pretty easily. So how would you find a unit vector then? Well, let me give you the definition, and then we'll do one. So a unit vector in the direction of V, I'll call V, say A and B, this vector, so I'll just give it general coordinates. You can calculate a unit vector this way. 1 over the length of V times A and B, or 1 over the length of V times V. Basically, you're just going to divide out the length in that unit, in that vector. And you're going to scale it down to make it equal to 1. Problem number 50 is a good example of something like that. in 50, they give you negative 5i plus 12 times j. Sir?
Can you say that again with the
Sure.
unit equals? Just say what that says.
Um,
You understand?
yeah. Let me show you with a little diagram. So let me finish writing this. B. Let's think about the vector negative 5 and 12. So we'll draw ourselves a little graph. So I've got a distance of negative 5 here and 12 here, right? This is negative 5 and 12. So this vector points out somewhere in this direction. Starts at the origin. So you've got a magnitude, which is the length of this, and a direction, which is, some angle with the positive x-axis. What we want to do is we want a vector that points in the same direction. Well, that doesn't. Here, let me see if I can't get a better word for that. Hopefully that's a little bit more legible. I want one that's shorter. In fact, how long do I want it? I want this to be a length of 1. But it's going to point in the same direction. So how do I scale this down? So I have, this is my v right here. I want a vector u that points this way, but it's shorter. It has a magnitude of 1. So that's what we're looking for. Something that's a little bit shorter. Or sometimes we have to stretch it, make it a little bit longer. Start by calculating the length of v. How long is that vector? So I'll give you a second to work on that. I'll give you a hint. It should work out pretty nice and even. If you're looking at a number, a certain squared number, and you can't remember what it is, on the left-hand side board, you've got a little bit of a cheat sheet here. It's got the first 20 perfect squares. Or you can hit the square root key on your calculator, either way. Ahmad's got it. But who all beat Ahmad? Who got it faster? 13? Good deal. So the calculation should look like this. Negative 5 squared plus 12 squared. 25 plus 144 is the square root of 169. So the length of v is 13. That's great. We wanted to create a unit vector that points in the same direction as v, but it's a little bit scaled, so that this length is going to be a length of 1. So u would equal 1 over the length of v times v, or 1 over 13 times negative 5 and 12. Now sometimes people leave this out here. Sometimes you distribute it to both terms. You could write it as negative 5 over 13 and 12 over 13. Let's double check it. What would I have to do to calculate the length of u? Maybe what should I do to calculate the length of u? Here's u, right here. Some help? Basically, this works back to the Pythagorean theorem again, right? This is your a, this is your b. So it's just a squared plus b squared. Negative 5 over 13 squared plus 12 over 13 squared. 25 over 169 plus 144 over 169. Let me pull out my Texas Instrument here. So its length is 1. And that's what we wanted. So we've got a vector that points in the same direction, but its length is 1. So we've got a unit vector. Hans? This is just checking it. Yeah, this is just checking it. So the answer to the problem, though, and I appreciate your question here, this is the answer to the problem right there. That's our answer. This is just the check, as you said. Thank you. Are we okay with 50? Do you want to do another unit vector? Yes, Sri? Correct. Correct. Just the positive root would work there. Charbel? You want to do one more? Sure. Let me take a look here for one. Do you want one that works out even, or don't you care? Don't care? One that works out even. All right. I'll give you a heads up. We'll do problem number 48, but the answer doesn't work out nice and even like this last one. But it's still workable. Just find V and write it like this. There's nothing wrong with writing it like this. This is an acceptable answer, just like this. So really, if you just write 1 over V times V, hey, that's good. Sometimes it's convenient to distribute it, other times not. In 48, our vector V is negative 3I minus J. And equivalently, you could write that as negative 3 comma negative 1. That's another way to write that vector notation there. You can distribute that to both of those terms. That would be okay, but you don't have to. Really? Oh. All right. You know what? All right. Part of the reason why I'm getting something different than you is that my book has the answers in it, and unless you're looking really carefully, It looks different than what I said. All right. So, all right, we've determined this is not problem 48. It's problem 48-ish. Ish. Yeah, I use ish a lot. But regardless of that, let's move on and find the length of this thing. So it's going to be negative 3 squared plus negative 1 squared, which gives me the square root of 10. My unit vector is going to be 1 over the length of v times v. So 1 over the square root of 10 times negative 3, negative 1. And that's it. That's all you have to write. That's fine right here. If you want to be really thorough or different, whatever it is, you can distribute that. That'd be negative 3 over the square root of 10 and negative 1 over the square root of 10. But this is a scalar. It multiplies both components of your vector. All right. I didn't hear and I'm lost, did I?
No,
Okay.
You're gonna stop here.
Oh, okay, good. All right. No, this is fine. There's nothing wrong with that. Sometimes maybe it's more convenient to write it like that, but if I ask this on a test, I would accept either of these two circled answers. Do you want to check this one?
No.
Check it, make sure it's length 1. Very good. You trust me? Hey, I appreciate that. Thank you. I've said a few times here today that vectors have a magnitude and a direction. Sometimes we're going to rewrite those vectors given our magnitude and direction. So we'll start out with problem number 58. 58, we've got a vector. The length of the vector is 8. And it makes an angle with the positive x-axis of 45 degrees. Alpha equals 45 degrees. Our goal is to write it in this notation, a comma b, or like this, where I and j are your unit vectors. Okay, so if you want to borrow some rulers, I've got some up front here. Let's draw this first of all. So a 45-degree angle, that's going to be in the first quadrant. And that's pretty close. This distance here, the magnitude of v is 8. That's 45 degrees. If I want to know what A is, or if I want to know what B is, then I'm going to have to do a little work here, a little trigonometry. I know the length of this side is 8. That's what they told us right here. The length is 8. How would I figure out the length of side B? What would you do? SOHCAHTOA. Good thinking. So this side is your opposite side. We know the hypotenuse. So something that involves your known angle, the opposite, and hypotenuse in a right triangle is the sine. Sine of 45 degrees equals, call it b over 8. If I multiply both sides by 8, 8 times sine of 45 is 8 times the square root of 2 over 2, or 4 square roots of 2. So, opposite side, that's your height b. Opposite over hypotenuse is the sine. So that's b. 4 square roots of 2. I heard a what is. Finish your thought. 8 times the square root of 2 over 2. Sure. How would I figure out side A? Jeff? Any suggestions? All right, cosine of 45 equals a over 8. And just like the previous one where we calculated b, cosine of 45 is square root of 2 over 2. So a is 4 square roots of 2, just like b. So we've turned a from a magnitude and a direction into a vector with two components. So the vector is going to be 4 square roots of 2 and 4 square roots of 2. Equivalently, you could write it as 4 square roots of 2 times I plus 4 square roots of 2 times j. Or even fancier, 4 square roots of 2 times I plus j. I really don't have much preference from one versus the other. If I do ask you for it in the form of a plus bi, then yeah, I want it like this.
Couldn't we just say this is a 4590, so both sides should be equal, and then once we figure out the first one, the second one should be the same?
True, but in general, we're not always going to have the good fortune of dealing with a 45-45-90 triangle. But yeah, in the case that you do have that, then once you have one, essentially you have the other, because they're going to be the same.
I'm saying, would you consider that as a...
I guess I'd like to see one of these. I don't have to see both of them, but in the case of a 45-degree angle, I'd probably like to see one of them. Let's try another one. And, in light of your question, I'm going to change things up a little bit. I'm going to do problem number 60 as opposed to problem number 62. Problem 60 is going to give you another 45-45-90 triangle. The only difference is that this 45-45-90 triangle is going to be in the fourth quadrant. So you can kind of get away with what you were suggesting, but you have to be careful about the signs because one of them is going to be negative, one is going to be positive. So, yeah, problem 58 was a nice warm-up problem. But problem 60 is a good follow-up. Is there anything else on 58 that maybe you're uncomfortable with? Hans? Mm-hmm. Yep. So, let's see if I can... No, I don't want to take the time to try and do that on decimals. You can, but let's just move on to problem 60. This time we got the length of our vector is 3, and the angle that it makes with the positive x-axis is 240 degrees. Okay, so let's draw that. What quadrant is this angle going to be in? Third quadrant. Good deal. So we've got an angle of 240 degrees. 240 degrees, which means there's a 60-degree angle in the third quadrant. The length of this is 3. We need to determine two different things here. We need to determine the length of this side here, call it A, and the other side B. So let me use a little color to demonstrate these. This is going to be A, and we'll do B in blue. So we need to figure out both of these sides. Now you can use the reference angle or you can use the entire angle. It's up to you. Figure out A, the x direction, and B, the y direction. This is just an application of material from section, I think it was 4.1, right triangle trigonometry. Wish my IT guys would figure out a way to give me a pause button. So much easier. Totally is. Just leave it like, you don't have to, there's nothing fancy you can do, just leave it at that. The map? No, I don't. Sorry. I'll send her an email, but yeah, last year took it until December, so I wouldn't be surprised. Believe me, I have reasons to be just as anxious if more than you to get those back.
This is weird. I feel like I did one.
You should put in an exact value for sine of 240.
Okay.
It's one of those special ones on the unit circle.
Is it? So we're using sine or cosine?
Well, it depends on which one you're trying to find. If you're trying to find B, B's the opposite side of the hypotenuse, that would be sine.
Or
Sine is opposite over hypotenuse. Cosine is adjacent to hypotenuse. So,
So it doesn't matter which one you do
well,
first.
no, it doesn't matter which one you do first. You need to go for it. I mean, you can. Let's see if I choose sine. It's an opposite over hypotenuse. You have to be over 3. Sine of 240. And your cosine is adjacent over hypotenuse. So here, 3 over B equals cosine of 240. So what's the sine of 240? Another pi.
Oh.
Well, it'd be 4 pi over 3 if you're thinking about the angle in radians. Okay, good. Same thing with the sine. Excellent. So we'll start out by calculating B. B is the opposite side. Opposite over hypotenuse is which function? So the sine of 240 equals B over 3. If I multiply both sides by 3, 3 sine of 240 is really 3 times negative root 3 over 2. And that's it. Negative root 3. Negative 3 root 3 over 2 is b. What about a? Now a is not going to be the same length as b. We can't get away with any shortcuts like we did with, or could with problem 58. So we'll do with cosine of 240 is a over 3. 3 times cosine of 240. What's a cosine of 240? Negative 1/2. Oops, that'd be a. So there's your a and b in kind of an angled bracket vector form. You could write it like this: negative 3 over 2 and negative 3 square root of 3 over 2. Or you could also write it as negative 3/2 times I minus 3 square roots of 3 over 2 times j. So a couple different options. It depends on what you're being asked for. In this case, I think they were asking for the latter. They were looking for this form is what they were looking for in this particular problem. Were we feeling a little more comfortable with that one? Okay.
How can we use, I mean, other than 40, what's another option of not using 40?
All right, so it's a good question. What if you just said, you know what? All right, I know that this angle is 60 degrees. And you deal with the sine and the cosine of 60 degrees. The sine and cosine of 60 degrees are both going to be positive because you're in the first quadrant. All you would have to do at that point is adjust the sign of these things for the quadrant that you're in. So, for instance, if this was a second quadrant angle as opposed to a third quadrant angle, then you say, okay, well, I know to make the x-coordinate negative and the y-coordinate positive. If I was down here in quadrant 4, x-coordinate would be positive, the y-coordinate would be negative. So you can use the reference angle, 60 degrees. You're just going to be a little bit more careful dealing with the sign of what you're left with. So it's a good question. Thank you. Let's do one in the other direction. Let's start out with something like this and come up with its magnitude and direction. So an example like that would be problem number 64. They give us the vector v equals I plus square root of 3 times j. I and j for us are always going to be understood to be the unit vectors. Alternatively, you could write this as 1 comma square root of 3. Writing it like this makes it a little bit easier to graph. So here's a distance of 1, distance of square root of 3. It's going to be a little bit taller up here. Something like this. So 1 and the square root of 3. There's two things that you could be asked for. In fact, will be asked for. You're going to want the magnitude of v and the direction. What's the easier of the two to start out with? Magnitude. So let's start out with the magnitude. See if you can't find the magnitude faster than a mod.
2.
All right. You didn't beat a mod. All right. Square root of 1 squared plus square root of 3 squared is 1 plus 3. Square root of 4 is 2. So that's helpful. We can plug in a 2 here. I know that this is the square root of 3, just like it is over here. You've got a lot of choices, an awful lot of choices to find alpha. What looks easiest? If you're going to put this in your calculator, if you're like, look, I really just don't feel like thinking, what's going to be the easiest thing here for you? I'd say the cosine, right? Because it's going to involve ratios of this side and this side. So the cosine of alpha is 1/2. Meaning alpha is the inverse cosine of 1/2. What angle has a cosine of 1/2? 60 degrees. If you don't remember that off the top of your head, then at least pat yourself on the back for your clever choice of using the cosine here, because it's easy to type in the inverse cosine, second cosine inverse of 0.5. There is one thing that I would suggest here, that you be in degrees. You're not going to recognize the answer if you leave it in radians. So if I put it in degrees, yeah, it's 60 degrees. If I needed the answer in radians, I can convert it from there. Let's take a look at the answer in radians. What would the answer in radians be? What does that represent? I mean, it's just a decimal to me. Yeah, it's pi over 3. Hard to see that, isn't it? It's hard to look at that and go, whoa, yeah, that's pi over 3. I mean, if you really wanted to force the issue, you could. You could divide it by pi and then hit the answer to fraction key and say, oh, yeah, that's 1/3 pi. But that's an awful lot of work. I think I suggest this way, the best. A couple problems to finish up with. And they go back to your handout. So let's go all the way back here. And look at problems 18 and 20. 18 and 20 are actually a couple of true-false. You could do these if you actually assign some quantities to the vectors, but I think we can do it just as well without it. Problem number 18 asked, is k plus g equal to f? True or false? Well, let's start out with vector k, which is right here. If I move k and then move g, is that the same as vector f? Almost. Vector f points the wrong direction. Vector f would have to have a tail here and a tip here so that you can start out here and end up the same place that you do when you add k plus g. So this would be false. So the direction matters. Yes? Yeah. Or another way to make this true would be k plus g equals the opposite of f. That would be true. The opposite of f would start out here and go to here.
So Jeff, can we like put it in motion and say that vector k is a force pulling down, vector g is a force pulling left. So logically, it has both of them. They has to pull left. They have to pull left. It cannot be go right.
Well, if you wanted to think of it in terms of forces, a force pulling down or a force pulling to the left would result in something pulling down and to the left.
Right.
It would be
That's
both
what
of them.
I said, yeah.
Okay.
So they can't be going right. because
So
they're
it can't be up and to the right if we're pulling down and to the left.
Right.
So let's look at problem number 20. G plus H plus E, is that equal to D? So if I start out here and move H, and then I move G, and I move back E, is that equivalent to D? Am I going to get the same place? Start out at H. Oh, let's see. Did I copy these down the wrong order? Oh. Actually, yeah, no, this is in the right order. But if I add h and g in any order, I'm going to get over to here. Vector e is going to take me back over to here. That's equivalent to vector d. So a couple of you are saying that that's true, and you're correct. Yes, Sri? Actually, well, as long as you're getting to the same place, then they're equivalent vectors. Yes. For homework, try 17 through 61.